Hi everyone, we're going to finish off stereochemistry, and I brought Ginger because she loves optical activity, and she would love to learn about this too, so, well, maybe not. So here is a drawing of two enantiomers. So if you look at them, the chiral center, can you find it? It would be right here, and you can see where one of these is wedged and the other one is dashed right here. Okay, this is called carvone, and it's present in various essential oils. So for this one, our carvone is actually gives the flavor of spearmint, and S-carvone is in the essential oil of caraway seeds, which is usually in rye bread and things like that. You can see that even though they differ in their configuration at that carbon, whether it sticks out at you or sticks behind the plane, you can see that their melting point is the same, their boiling point is the same. So that might lead you to think, well, how do we even know if we have stereoisomers if their physical properties appear to be the same? Remember, these physical properties are based on connectivity, the kind of functional groups the molecule has and its intermolecular forces with the other molecules of it, like itself. So it turns out that there is a way that we can detect enantiomers, and even what percentage of a mixture is one enantiomer over another. Now we're not going to go through that quantitatively, but I'll just sort of show you the basic idea. This is how we measure or how we determine whether we have one enantiomer or the other, assuming that it's a pure mixture. So you've got a light source here, and you've got light going in all directions. It's an electromagnetic wave. The polarizing lens will filter out a certain direction of that light. So let's say the rays going like this. And those will go through, and then you can see when it hits the sample, these are where the molecules are. That light will go through it in a certain orientation and get rotated from where it started. So if it's straight up and down, when it goes through the sample might cause that plane of light to get rotated. And then the outgoing light gets measured in terms of how much it rotated, that plane of light, and we can measure that rotation. So here's an animation on YouTube that I really like. You can just Google or YouTube search polar emitter stereoisomers, and you can see that it's demonstrating right here that you've got these electromagnetic waves going in many directions, and that when it goes through this polarizer, that only one plane of that light goes through, and as it rotates around you'll see that more. So these are going in all directions, light waves, and these are the one plane of light. So it's a filter. But now with that one plane of light, we can see how a sample of molecules can affect the rotation. And if you take a look here, I'm going to pause it, you can see that through this cuvette you see light going in, and then it gets twisted. So it rotates, let's say it's rotating counterclockwise if my eye is over here. This sample is rotating it the other way, so that tells me it's something else. And in this case, you can see though that this rotation going counterclockwise is balanced by this rotation going clockwise. They're actually rotated the same magnitude but different direction, clockwise versus counterclockwise. So this is actually what happens when you have stereoisomers or optical isomers, where you have the rotation of light going one way versus the other. So they're different in their direction of rotation. And we call them optical isomers because they have this property of interacting with light. And that's not true for all stereoisomers, but we're talking about enantiomers here. So as you saw in the simulation, you've got the rotation of light occurring in opposite directions, but the magnitude of that rotation was the same. So if we look at carvone here, We've now added some more physical properties, which is the optical rotation. And one is negative 61 degrees, whereas the other one's positive 61 degrees. So the fact that they're the same value tells me that's the same type of molecule, carbone, but you've got the two different stereoisomers or optical isomers of these, one going negative and one going positive. Negative means they're going counterclockwise, which is, or going to the left. So I think of that. Left is levorotatory, actually. And then dextrorotatory is the other one that's going positive. So if we label that on here, you could have this be called negative R carbone, and this would be positive S carbone. Now we're going to go through S and R separately. That's the next part. This is also called L, and this is called D. So I could mention L carbone and D carbone. It's another way to tell us which stereoisomer it is. Now, one thing that you might want to think about is that the light might be going through not a pure sample of one isomer or the other, but actually a mixture of the two. If it was a 50-50 mixture, then half of it would be rotating one way, the light, and the other half would rotate the light the other way. And what you see is an optical activity, by the way, it has a symbol of alpha. The optical activity of that would cancel out. So the optical activity of a 50-50 mixture of these optical isomers would be 0 degrees. And then if you didn't have a 50-50 mixture, by the way, that term 50-50 mixture of enantiomers is called a racemic mixture, and that's going to be important vocab in the next few chapters. So racemic mixtures, if you didn't have a racemic mixture and you had more of one than the other, then it wouldn't totally cancel out to 0, and you could measure how much is the resultant change, and then calculate. If you knew what it would be pure, you could compare, and you could calculate what mixture might be one over the other. That's called enantiomeric excess. But we're not going to go through those calculations, but if you're taking the DAT or the MCAT, these kinds of questions might come up. So I'll just let you know that it's not something I see a lot, but you might see that in the future if you did want to learn that on your own. Now let's talk about R and S. This part in the name also tells us about which stereoisomer we have, but it's not related to the physical property of optical activity or optical rotation. So the negative and the L go together, the positive and the D go together. I could say positive carbone or I could say D carbone. But it doesn't tell me on paper how to draw it. So there's a separate system for that. And that's called absolute configuration. So regardless of how the light is rotated, I need to be able to communicate or draw what kind of stereoisomer it is, because I might not have a catalog in front of me where I know its physical property. So I want to just be able to draw stereoisomers and give them a name. So here's the system for that, and so here's the system for R and S configuration. And I'm going to emphasize, I'm not looking at what the optical rotation would be. I have no idea what it's going to be for 2-chlorobutane for this stereoisomer versus this one. So what I really want to go off of is, how do I get you to draw this one as opposed to this one? There's a system based on the same kind of stuff as E and Z from the double bonds that we were learning a few weeks ago. So the system is to use the same kind of priorities we did before, where we look at all 4 groups attached here, and then there's the implied hydrogen in the back. So I'm looking at the 4 groups attached to this carbon, and I'm going to give each one of them a priority number, and it's going to be based on mass. So here I have chlorine versus carbon versus hydrogen. So chlorine is the heaviest, so that's my first priority. Then the next person over here, carbon or hydrogen, these carbons win, so over the hydrogen, but which carbon would win? And I think you see that this carbon's next heaviest one is another carbon, and this carbon's next heaviest atom is a hydrogen. So this carbon would win. So we're not adding up the ethyl group, we're just looking one atom at a time down the chain until, we get someone to win. So this carbon is number 2, this carbon is number 3, and this hydrogen is number 4. So number 4 is usually hydrogen, but if there's no hydrogen, then you just go with whoever is the lightest. All right, now that we have this down, you want to try to rotate the molecule such that priority number 4 is behind the plane. And we are lucky because it happens to be hydrogen, which is dashed or behind the plane. So now I'm going to look at the direction of this. And here's where I don't want you to get this confused with the optical activity we were talking about. This rotation is not necessarily the way that the light gets rotated. So this is 1, 2, 3. So like that. And I have a simple rule for R versus S. So this is R if 4 is in the back and we have 1, 2, 3 going clockwise. So that's going to be called the R stereoisomer or optical isomer. So I'm going to put an R here in front, R-2-chlorobutane. Now if it was going counterclockwise, then it would be called S. So now let's look at the next example over here, and we'll see how it's different. So I take my chiral center, and I go 1, 2, 3, and my hydrogen's in the front 4. So 1, 2, 3, and we already went through which would be 1 through 4. And now I see that 1, 2, and 3 are still clockwise, but 4 is now in the front. So I'm actually, if I wanted to compare it to this, I would want 4 to be in the back, right? So if I push the 4 in the back, this whole molecule would rotate, and then I would be looking at 1, 2, 3 going the other way. So picture this. I'm looking at 4 in the front of me, which is in the back of you. And when I see it, I see 1, 2, 3 going clockwise to me. But what's that going for you? You're seeing counterclockwise, okay? So what I want to do with these rules is make it easier for me to figure all that out. I'm going to say, well, when 4 is in the front, then I'm going to reverse the rules. So that means 1, 2, 3 going clockwise before was R. Well, if my molecule's flipped over, I got to say 1, 2, 3 going clockwise is S. So this is going to be S2-chlorobutane. So 4 in front, 1, 2, 3 looks clockwise. Normally I would say that's R, but because R is in the front, or 4 is in the front, so I got to reverse that to S. Let's do one more together because it sort of takes a while for this to sink in. Okay, if you want to pause it and try it yourself, go ahead and do that. But I'll just go through it just in case you want a little bit more practice. Here we have chiral center. It's not like I know if you're pausing it anyway, but I hope you are. I hope you pause it and try some of these on your own and then check instead of just letting me do them all. Okay, so this one, it's got some double bonds, so that's good. So I'm going to draw in all the groups and do the priority. So 1, 2, let's see. So carbon, 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 they all tie. So we look at the next heaviest one on each. So this one's going to be oxygen. Now this double bond over here actually counts as if it were 2 single bonds to oxygen. And then because they're bonded to carbon, you sort of extend that back to the carbon again. Okay, so a C double bond O expands out to 2 single bond O's, and then they're attached to C, so you come back and you put a C on there as well. So that's sort of weird. So we've gone from, I'll do the secondary ones in a different color. So originally these tied, and then I'm looking at the next heaviest one on each. And so they tie as well. They're both oxygen. So I come back to here and I look at the next heaviest one, which are these. And of course this one's lost because it's only got hydrogens. Now between those they tie again. So 2 oxygens here, 2 oxygens here. So I go back to the main one again and they send their next heaviest one. This one's got a hydrogen attached. This one's got another oxygen attached. So this one wins. So this is number 1 over here. This one's number 2 because it had 2 oxygens. This one's 3 because it had no oxygens and just hydrogens. And then my hydrogen over here is 4. All right, so now 1, 2, 3, that's going counterclockwise, and 4 is in the back. 4 is in the back. Counterclockwise is S. So this is S dash, and you can put that in parentheses, S dash 3,3-dihydroxy 2-methylpropanoic acid. So if I wanted the R isomer, I would have to switch this group somehow. So either I would switch these 2 groups or I would put this methyl group in the back. So here's a really simple way of drawing the R version. I would tend to just copy the skeleton here. So everything in the plane sort of stays in the plane. It reminds me of the rain in Spain, stays mainly in the plane. This is HCH3, My Fair Lady, if you don't know. All right, so here I just switched these. So there's plenty of practice here, and I want you to try these, and I do want you to notice there are 2 chiral centers in some of these, so go ahead and do both chiral centers. And then this one is a little trickier because it's the Newman projection. So see if you can convert that, just like we did in our last session. Convert that first and then figure it out. Unless you can see it in the Newman projection, that's fine too. All right, let's check our answers soon. Okay, we're back. Let's take a look at our ibuprofen here. 1, 2, 3. This one's a little tricky because you've got so many things going on here with these double bonds, but ultimately you have 1 carbon here, and then they tie, and the next heaviest one here is oxygen, and the next heaviest one here is carbon. And no matter where you go, and you've got this double bond, so it's actually an extra carbon here, but carbon still loses to oxygen. So this is 1, 2, 3. Even though some students see number 2 as being this big group, so doesn't that have to win? And the answer is no. You only go 1 atom at a time. Whoever's heavier wins. So this is 1, 2, 3 counterclockwise. But remember, the hydrogen here is number 4 in the front. So you really think of it as going clockwise. Here, this one's tricky because you've got carbons. Well, first you have oxygen here, so that's got to be 1. And then you've got hydrogen here, which is 4. And sorry, my bad, I should put an H there. And then you've got 2 here, which are carbons. Now, this one looks like it wins because it's got this double bond, so it's like having a carbon here, here, and here. However, this carbon's next heaviest hitter is the nitrogen, so this carbon wins over this one because it's got a nitrogen. So this one's 2 and this one's 3. So 1, 2, 3, that's counterclockwise, but 4 is in the front, so we got to switch that to clockwise, which is R. The next one has 2 chiral centers. So I did one of them in blue. 1, 2, 3, that's R. And then number 2 here, this one is in purple. I have 1, 2, 3 going this way, and my 4th one is in the front. See, there's a wedge hydrogen here, so I got to switch that to S. When you have 2 chiral centers, we usually like to put it in the front here with a designation of which carbon. And the number for the carbon is based on IUPAC nomenclature. So if my chain is numbered such that it's 1, 2, 3, 4, 5, because the alcohol will get the lower numbering. So this is 2, R, and this is carbon 3, which is S. Same thing here for this one. Let's look at this chiral center first. 1, 2, 3. And this one wins because it's got, it's got 2 carbons, whereas this one only has 1 carbon. So 1, 2, 3, that's R, but this is in the back, so that means the H is in the front, so I got to switch that to S. This one here, this one wins because of the oxygen, which is going to be the next winner. This one only has a carbon. So 1, 2, 3, going this way, counterclockwise is S, and hydrogen's in the back, so it can stay S. Again, with the numbering, we number the alcohol 1, 2, so 1S, 2S. For this one, we have a complex chain. If you look at the name, 3-methylcyclopentyl propan 2-ol. So they're saying this is 1, 2, 3. And so carbon 1 has this complex chain. So I should have put a 1 dash parentheses, so please fix that on the handout. 3-methylcyclopentyl, that's referring to the complex chain, so that goes in parentheses. Now there's 2 chiral centers, so this one's a little tricky in how to put that into the name. Here this is S, but it's hydrogen's in the front, so I had to switch it to R. This one is just R, but switch it to S. And then for the name, this is the parent over here. This is the complex branch over here. So the way that it's being named is 1, 2, 3, and here's my propan 2-ol right there. And then at carbon 1 is this stuff over here. That's my complex chain. So I want to say that off the parent chain, I've got an R configuration. So I'll just put R. And I don't put 2R because there's just this one R here. So R. And then the S is referring to this methyl group. So I just squeezed it in here. 3S-methylcyclopentyl. Okay, it's not a big deal. As long as we can communicate with each other, it's fine. And then here, this one's tricky. Depends on where you put your I. I like to redraw the Newman projections, but some of you might be able to tell just from here what these might be, but I think it's a little tricky. So I redrew it in this form, and then so I put my I here, and I saw hydrogen on my bottom left and methyl on my upper right, if my eye is here. So my face is right here. And so here's hydrogen on my lower left and methyl on my upper right. I see chlorine on my left going up, chlorine on my right going down. Okay, so I'm looking, instead of head on, I'm looking sideways. After I redrew it, I figured it all out. This one's going clockwise, but hydrogen or number 4 is in the front, so I just switch it. And this one's going this way, so that's R. And so I put, for the numbering, it's sort of ambiguous, right? Because you could go 1, 2, 3, 4, or you could go 1, 2, 3, 4. And in fact, there's something funny about this molecule. Do you guys realize what's going on here? Take a look at this molecule. Does it look like anything we've seen before? If you guys rotate around this bond, you'll see that this is actually meso. Let's do that. So here it is redrawn, and I've rotated it so that this chlorine comes up here. So that means these guys, this swings in front and this goes to the back. So now you can see that there is a mirror plane of symmetry here. So it really doesn't matter. This could be 3S, 3R, or 2R, 3S. And it doesn't matter because either way, it's going to give me this molecule. This is meso, which means that it's achiral. Now, achiral molecules do not rotate plane polarized light. So it's very similar to having a mixture of 2 isomers where one rotates one way and the other rotates the other way. These 2 centers would cancel out. So these are not optically active. So I'm just going to put a note here that this is achiral. But we still want to know the R and S because there might be a stereoisomer of this that is chiral, right? Because all I have to do is change these 2 groups and now it's chiral. So I need to know that it's the achiral one versus the chiral one. So that's why this designation, absolute configuration R and S, is important. So quick recap of today. You have enantiomers. They have the same everything except for configuration about their chiral center. The way that you can tell physically that you have two different ones is by looking at their optical activity. Optical activity can be measured with the polarimeter, and you can measure something called the specific rotation. So let's say we have two enantiomers here. You'll notice that one has a specific rotation of one direction, negative or positive, depending on which direction, counterclockwise or clockwise, that light gets rotated. Instead of negative, you can say L, or instead of positive, you can say D. If you have a 50-50 racemic mixture of these enantiomers, then the net specific rotation will be 0. That has no relation to drawing these molecules on a piece of paper and knowing whether you have the dash or the wedge. So for that, we use a different system called absolute configuration, and we use R and S. To determine R and S, which again has no relation to D or L or positive or negative, we use a system of going clockwise or counterclockwise based on priorities. These are the Kahn-Ingold pre-log rules, so they're based on mass. We practice that, being able to identify the chiral centers and whether they're R or S. And finally, if you have achiral molecules, even though they might have chiral centers, which are called Meso compounds, they are technically achiral, so you will not have any optical activity there. Your goals should be to practice identifying the chiral centers and determining R and S. And in terms of optical activity, you should know achiral molecules are not optically active. Optical isomers or enantiomers have the same magnitude but opposite direction. And a racemic mixture has an optical activity or specific rotation of 0.